Hello, and welcome to the Compy SJSU SJ2 methodology. In this, we're going to discuss how you're going to go about designing software for the SJ2 framework. So a bit of an overview. We're going to go over the SJ2 board overview. So we're just going to go over what it can do and what it's capable of. We're going to go into the software design, what you should consider when you're designing the software for SJ2. The project structure. So now after this, you will hopefully understand the bulk of what the different folders and why they're set up as the way they are, and just what they do and what's in them. Testing and verification, and finally, Git workflow. So let's start off with the SJ2 board overview. The SJ2 development board comes with, it's an embedded systems development board for basically educational use. It utilizes a modern processor, utilizes a ARM Cortex M4F. F stands for the fact that it has a floating point unit. The previous one did not have a floating point unit, so you had to do all of your floating point math in software. The LPC 4078 microcontroller includes GPI peripheral, PWM, quadrature encoder peripheral, a nested vector interrupt controller system, an analog to digital converter, a SPI serial interface, a I2C interface, a YOR interface, a real-time clock peripheral built in, and a lot more. You can go into the datasheet for the LPC 4078, which I'll give the information for where the datasheet is located inside the project, to figure out all the different things that it can do. Next, we're going to go over the board features. So that was just the chip that's actually located here. Now I'm going to go over the things that are included with the board. The board includes 4 controllable LEDs, 4 readable push buttons, an SD card reader, a real-time clock battery holder, an OLED display 128 by 64 pixels, an accelerometer, temperature sensor, gesture sensor, and the gesture sensor actually comes with additional usages. For example, it'll be able to figure out if you swiped left, right, up, down, or towards it. It can also figure out proximity for a short distance. It can also do color. Along with that, we have an external SPI flash memory interface. So if you wanted to, you could hook this up to a SPI, like another flash memory that talks over SPI flash, talks over SPI, and you should be able to talk to the one that's on board. It's actually this chip right here. The ESP8266 Wi-Fi port. The area that's kind of obstructed here, so it's no longer visible. This area here holds a ESP8266 Wi-Fi port, and just allows people to be able to give their SJ2 Wi-Fi capabilities. And then on the right-hand side of it, you'll have the 40-pin expansion port, which will include things like ADC, DAC, I2C, the infrared receiver pin, and so on and so forth. Another capability that this thing has. Out of those pins, around 35 of them are additional GPIO. So I'm going to go a little deeper into the software methodology. So technologies used, how the code is written, and what to avoid. So we have actually quite a few technologies that we use for this. We use C++17, a modern version of C++. The idea that C++ is slow is a myth. You can actually generate extremely efficient, extremely powerful code by utilizing the things that the language gives you in C++17. Lambdas would be a good example. The extended templating is another good example. Constant expression is one of my favorite things in this in C++ 11 and above. Actually 14 and above, because 11 it was too restricted. But I digress. Python. It's used sparingly, but it's used for code generation, for parsing work. It's also used as the backend server for telemetry, which is not part of this project, but does use Python. So does Hyperload, and so on and so forth. Make. So make is used to compile all of our source code into executables, as well as do our unit tests. Clang format will format our code to our standards. Valgrind will, if we ever do end up using any usages of malloc, which we'll go over in a little bit, Valgrind will be able to detect memory leaks if they exist via the unit tests. And then G-coverage. It is used to create coverage reports for the code that we develop. More on that later on. Going further, we use the ARM none EABI GCC. None means no architecture, like no operating system. EABI stands for extended abstract binary interface, and GCC is the compiler. OpenOCD is the open on-chip debugger, and using the Seeger EDU chip, you can work with it in order to debug your firmware, step through your code, and all that. GDB to be used with OpenOCD to be able to debug and step through your firmware. And lastly, I believe this last, Doxygen. Doxygen is how we'll be going about generating source files, not source files, documentation for our code. So the way that we'll go about doing our comments will be in a Doxygen format such that it can read our comments from our code and generate source code for us. Now, the code will be written in C++17, and here are some things that you need to consider. One, we'll be having a heavy use of objects and classes. There'll be constant consideration for code size, constant consideration for code speed. The system should be as environmentally agnostic as possible. For some low-level drivers, you can't really get away from the fact that you need to communicate with the registers. But for any composite drivers, you should be able to move out different modules or different low-level implementations, as long as the class meets the same specs of methods that you need, has the same API. You should be able to swap those in and be able to use them anywhere. It should be able to be written and runnable on a host machine. The code must be independent, so there shouldn't be extended amounts of dependencies as far as possible. So you want to make sure you keep your code as independent as possible. Code should be as modular as possible. Code style should conform to the Google style guide. And one interesting area here is code assertiveness. Interesting about code assertiveness is the fact that, what I mean by that is that we will be using assert quite often. Anytime a user does something wrong in our libraries, the way forward is to, especially during initialization, is to stop and assert that a particular thing has happened, and to just null and basically put yourself into a while loop, basically run an assert. The idea here is that if anyone, before the program gets running too far into and beyond the initialization step, we should stop the user and tell them they did something wrong, rather than trying to make our code flexible and doing some type of black box fixes to make it work. The first step should be stop the user. Beyond that, as we're in the running time, it should be less assertive. We should favor composition over inheritance. Deep inheritance chains cause quite a bit of headache. It spaghettifies your code. It also can result in very large objects. So we want to stick with just composition. We must only use static memory for the libraries that we design. malloc has been set up for the library here, but almost all the code that we write should be using static memory. You should not be using new. You should not be using malloc as much as possible. And then favor dependency injection over hard dependencies. We'll be going over this a lot more in the testing workshop. But the base thing here is that you should be able to give your class any implementation of GPIO that you want with any functions that it's running, and it should not break. It should not be dependent on the specific GPIO module. And in the case of registers or peripherals that end up working with, or classes that end up working with peripherals, the idea here was that you would actually pass in the pointer to that particular structure through the constructor, but it should be a default it should be a default parameter, such that if the user does not supply one, we will supply our own. But if the user does supply one, which will only really happen during tests, we will then use that to our benefit. So what should we stay away from? So for the most part, we should stay away from C++ libraries, objects, and algorithms, such as string and IOStream, because of the fact that they use malloc and such like that, and the implementations of these libraries is magnificently large. So to keep away from that, or in order to reduce the size of our executable, we stay away from these algorithms. We'll either be implementing our own versions of them or alternatives to them. When possible, try to stay away from the usage of double precision numbers. We have a floating point unit that's only single precision, so it actually becomes very quick to be able to do math with single precision numbers. But if you need to store it at a higher precision or do work on a higher precision, that's fine. But you should do it sparingly. Now, I love class and function templating, and there are actually cases where using class and function templating makes for very extremely powerful code. If you use it in const expressions, it's almost, you lose nothing for that. But if you define a class or a function to be templated, For example, you have a templated function that adds two numbers together. It doesn't really care what type it is. The issue is that if you use it all over the place in your code, you could result in a template explosion, which is basically when you have a large set of different types being used for your functions, and you end up having an implementation for each one. Keep in mind that if I do an add function that's templated with an integer and then also with a double, I'll have two functions for doing the addition, not just one. So that's the reason why we like to stay away from templates as much as possible for real code. Whenever possible, stay away from the define macro. Use inline or constant expression. If you don't know what those are, look them up on the c++reference.org. But otherwise, inline, constant expression have to fit the typical C++ syntax. Defines do not. And that can end up, to reduce the amount of headache that we have, we should stick with inline, constant expression. You may not use runtime exceptions, and you may not use runtime casting. Runtime exceptions, that library adds so much to the executable that it becomes way too large. Runtime casting also adds a lot of code in. So if you can, static cast, reinterpret cast, and const cast. If you don't know what those are, I recommend you look into those. Now, let's go into the project structure. So how the folders are kind of set up. So we're going to the root folder. What you'll have here is the config YAML file, which we'll kind of ignore, datasheet, docs, firmware, references, tools, and setup. The setup is a setup script. We have a README for the Git repository and for anyone who clones our repo. A makefile that's actually global. It's actually used globally across all firmware projects. Our license, the global environment sh file, and that would pretty much be it. We're actually going to dive into the other ones coming up soon, but you can kind of get from what their names are what they're meant to do. So in datasheets, we have a datasheet for every component that is on the SJ2 board. So you would not need to go somewhere else in order to find this information. It's all inside the repository, ready for you to use. In references, currently we only have one item in references, and that's the schematic 1.b version. And when we make the 1.c version, there'll be another schematic for that one there. We'll keep both of them in there just for anyone who might end up having a really old version of the board, or one of the original three. In tools, we have the tools such as CPP lint. So it's a C++ linter. Goes through your code and does static assessments of whether or not the code fits our standards. Flash Magic executable. So if you're running on Windows, you can flash your device using Flash Magic. This gets generated after setup, which is it'll download and install, download and extract the ARM GCC. Hercules, if you decide to use Hercules. Hyperload gets installed by setup. OpenOCD is there by default when you pull the branch. It basically comes up with a configuration file that's required for OpenOCD to run with the SJ2 board. PuTTY32, PuTTY64, if you're using Windows, you'd like to use PuTTY as your serial terminal. And then finally, also brought in and get cloned into this repository is telemetry. I would highly recommend you use telemetry when it comes to communicating with the SJ2 or SJ1, or really any other device that goes over serial. There are a lot of cool things that are being added to that project. Then the docs folder. Now currently the SJ2 repository doesn't actually include all this information, but it will very soon. But it'll basically include all the information that's required to generate the docs as well as all the doc information as well. And this one kind of takes up quite a bit of space, but the firmware folder. At the top here, we'll have the first project, the demo project, the Hello World project. It'll include a link to the environment sh file and the make file. It'll also include a source and just a single main.cpp file. Within this, you'll see in the build file that we have the binaries, the CAN-DBC, the compiled files, which ends up being the .o files, the coverage file, as well as the test files, and we'll show some examples of what those look like in a bit. Or the test executables, really, or test compiled. Here, and more importantly, we'll go into the library, in the area where a lot of your code will be written into. So we have L0 low level. L0 low level is basically the lowest level software that can set up and start the board, as well as all the different definitions for registers, for Cortex M4 information, GCC, and stuff like that, as well as the a starter UART 0 just to get things kind of running. After that is the L0 driver section. This is the area where a GPIO driver and SPI driver, basically anything that really directly talks with a peripheral or a set of registers, should be placed. The lowest level driver should be placed here, And this is the code that will be dependent on a particular register source, pointer, and we'll have a certain set of testing for people who work in L1 drivers. Above that is L2 utilities. So let's say that someone designs a really neat algorithm that does masking for you. If you build something like that, then you put inside the utilities. Telemetry we put into utilities, and so on and so forth. So code that's very agnostic just is algorithms that we would find really useful for our applications. L3 is HAL. This is the hardware abstraction layer. This would be things like the LEDs, the buttons, the accelerometer, temperature sensor, and so on and so forth. These are abstractions so that we don't need, these modules should be taking in and being composite of the L1 drivers, and should not have to really touch any registers at all. L4 application is the highest level software, so command line interface information, high level tasks, definitions will be placed here as well. So a lot of stuff that's kind of high level will be placed in here. And lastly, we have L5, well not lastly, but we also have L5 testing. L5 testing is basically the folder full of all the testing framework information. And these are some compiled object files from this compiled header. It'll come with a main.test. If you're designing a unit test, you shall not define a main anywhere. That will conflict with this main.test. This one just kind of gets left alone, and your files will be placed. Your testing files will be placed alongside the files that you create. Here are the linker scripts. This one actually needs to be deleted. And then newlib, which is basically the definitions for the standard C library for embedded README for this folder. And then lastly, the third-party files. So if you ever want to include a new thing, a new source of code into the project, you will need to put them inside the third-party area. So the FAT implementation, where we get it from, will be placed here. VRTOS will be placed here. Any testing frameworks we decide to add will be placed here. If there's any really neat algorithm that does something for us, it can also be placed here, and so on and so forth. And that's pretty much the layout of the firmware folders. All right, so we're going to testing verification, and that is the wrong number. One of my quotes, I don't remember where I heard it from, but basically any systems that are untested are broken. That is the law here. If you have not tested out your code, it does not work. That also includes manual testing, but if it compiles and can load onto the board and the board doesn't immediately crash, that is not an indicator that your code works. It might just be an indicator that your code compiles and that you can load it onto the board and that it does not crash. So for unit testing, what is unit testing? Well, unit testing is a software testing method in which individual units of source code and assorted control data, usage procedures, and operating procedures are tested to determine whether or not they are fit for use. I got that from Wikipedia. In layman's terms, you're writing code that tests code. Why unit test? Well, a couple things. It's an indicator for reliability. It also builds confidence about your code and can define the behavior that the code tests under. For example, if we run our software and we do all our unit tests and all the unit tests work, at least to the level in which we've run tests for, we can weed out situations that might be caused by hardware issues. If we know it's worked in the past and our unit tests still work, and none of the code hasn't really changed much, then we could probably push the blame over to other areas. It allows us to be able to isolate down to what areas might be causing issues, given updates that happen with the code base. It also builds confidence. So once you know that your code is fully tested and almost has nearly 100% coverage, you feel far more confident that the code that you have written will work as intended. And lastly, where do unit tests run? Well, they run on your desktop, laptop, local machine, whatever you're running SJDev on. It will not be running on the SJ2 board. It will be running on your local machine. So that's one of the reasons why it's important to make sure that your code is environmentally agnostic. So a couple of technologies. We have Cat, which is a unit testing framework. It's easy to set up. It's a single header file that all you have to do is include it and then you're good to go. It's easy to use. It's also very expressive. So here we have a very easy base test for datetime. I'm not going to go into too much detail here. You can look into Cat later on. I want to finish up this video. Later on we have FFF, which is Fake Function Framework. This is basically used to fake and spy on function calls. So if you were to pass a function as a callback to a class or to some object, you can figure out how that particular class went about calling it, what parameters it used, how many times it was called, a history of what arguments were called at what time, so on and so forth. And then here is a basic test of the terminal running a test, but right after this we'll also go into Fakelt, which is the object mocking framework for C++. With this, you can create a you can mock up and spy on existing objects instantly in a single line. So here we have some interface. It's a virtual int. It's a virtual function that is given it's a deleted implementation. We can implement this. We can define what we want each one of the functions to do and then run them. We can then pass those on into other classes and have them use those instead. So it's a great way to be able to, when you're doing composite tests, to be able to instantiate versions of the object that you want to use and use those faked versions of those rather than using the real versions that need to talk to actual registers. And now for code coverage with G coverage. So this is what it kind of looks like. Oh, actually, before I go into what it looks like, just to kind of make sure it's understood, what is code coverage? It is the amount of code that is tested or used during a program or a test's runtime. G coverage is like a new coverage tool that reports the total amount of code coverages per test, and it'll highlight lines that have been tested and executed. And the great thing about G coverage is that it also gives you a report as HTML, which we'll see in a little bit. So here we have it. Let's say we only had one test, our test CPP. We can go into this and we can actually notice and see that not all the lines have been reached, not all branches have been passed through. So we can actually see the areas that are highlighted red that state that they have not been touched, and there are areas highlighted in green that have been touched. Now we're going to Git workflow. I'm not going to go into too much detail because there's going to be a workshop on this as well. The idea here is that there is the origin, which in this case is actually my branch, which will hopefully just become a part of a Google organization soon, and then your forks. After you're done with your forks, you will make your progress. You will work on, well, in this case, you should have a master branch that you only use to pull in updates from upstream. You should have a staging branch, which is where you actually add in your updates sequentially. And then you have experimental, which you can do whatever you want with. You use that to just basically build and to experiment and do whatever you want. You can have as many branches as you want after that. But the staging branch will specifically have in order the set of separate small commits that will end up building up to your project. And once you have that, then we will take that commit chain and bring it into the project. It might be rather small. It might be rather big, depending on which project you're working on. But after you're done with that, you'll then go and do a pull request. Actually, you'll probably do a pull request after your first commit into stage. You do a pull request, and we will go through and we will evaluate your code, and we'll go through and do reviews at this point. And after we do a review and go through a review session, you should then go back to your branch, make the edits, force push it back up to your repository. That'll update the pull request. We'll continue to add more comments. And eventually, once we've looped through this multiple times and gone back and forth between fixing your pull requests over and over, then once it's pristine, it'll be moved into origin, probably into the unstable branch, and then from there moved into master when we find that it is properly stable with the rest of the code. So with that, that's pretty much it. Thank you for listening.